Hello everyone, we are Group 15. For our machine learning final project, we have decided to do a comparative analysis of machine learning techniques for handwriting digit recognition. So for this project, we have decided to use the NNIS dataset, which contains 70,000 images. We are splitting 60,000 training samples and 10,000 samples. Each of these images are labeled in one of the 10 distinct classes, and each image is composed by 28 by 28 pixels. So here we can see a level counting of each of the classes, and we can see that on average they have 6,000 for the training part and 1,000 for the test part. Here we can see one of the data exploration that we have performed. As we can see here for TSNA, with different perplexities, we have different kind of clusters. So for the pre-processing part, we have the normalization, which consists in divide the grayscale by 255, which convert the image in a binary scale of 0 or 1. And for the flattening part, is converting the 28 by 28 into a 1D vector of 784. So we have two parts for the evaluation. One is the supervised classification, which consists in the first method, which is logistic regression, while L1 and L2 regularization, and the bagging and boosting, in which we be implementing a random forest. For the second part is the dimensionality reduction, in which try to capture the most important characteristics with the less components.
So the first experiments that we're going to do is the logistic regression. We use L1 and L2 for regularization as well as ElasticNet. So with ElasticNet, what we will do is try different combinations of L1 and L2 to see what kind of result we can get. Now, overall, after performing the experiments with different regularization strengths and different mixtures of L1 and L2, we get these results. One of the most important results is the importance of regularization for having better accuracy. But in the end, when we do the F1 score for every digit, we can see that most of the models actually had very little difference when it comes to accuracy. Now, a very interesting result is we can see in the weights that the model learned for every class how some of them have done feature selection, while some of them don't do a very strong feature selection. In the case of L1 regularization, most of the pixels are near 0, but the best accuracy we actually obtain with the L2 regularization, in which some external pixels are actually still useful for the classification. Now, when we had an overfitting case, we erased too much of the less important features, and we cannot have a very good accuracy.
I'm going to cover ensemble methods, focusing on how we apply random forest and gradient boosting. For both models, we use the same pipeline and data format as the rest of the project, and we use a shared experiment function to keep training and evaluation consistent across runs. To keep the evaluation clean, we treated the test set as fully held out for the final scoring, and for boosting, we use a validation split for early stopping. First, random forest, we ran a small group to study how ensemble size and tree capacity affected performance. And we tested an estimator of 10, 50, and 100 with max depth values of 10, 20, and none. We can see the accuracy consistently improve as we increase the number of trees, and with depth none, it performs slightly better than 20 across the same tree count, reaching 0.97 test accuracy, and this shows that the largest forest improves generalization. Next, we have gradient boosting. We use XGBoost. Here we fix an estimated at 100 and a max depth at 6 to isolate the effect of learning rate. The results were strongly sensitive to this parameter. In 0.3, reach out our best boosting result at 0.97. So with that, we can say that higher learning rates give a better performance in our setup. And here we can see the tree ensembles significantly outperforms linear baselines and boosting obtain better accuracy.
Now we move to the optimization phase. Because most pixels in the image are black, we decided to apply principal component analysis. Our goal was to compress the data without losing the signal. Using the two most important components, we can see how the information is clustered already. Using 3, we can see the clusters in 3D. The question now is, how many components give us the optimal results? From our variance analysis, we noticed that we didn't need all 784 dimensions. We have reduced the dataset down to 154 components. That's a compression rate of 80%, while still retaining 95% of the original information. This set the stage for our models to learn much faster. The results were unexpected. The PCA model dropped accuracy to 95.02%, compared to the original's 96.96%. Surprisingly, PCA was slower to train, with 121 seconds, compared to the original model with 38 seconds. The lightweight model was the real efficiency king, training in just 9.5 seconds with 95.8% accuracy.
Now, after finding out that PCA didn't actually help with this, with the improvement of the training of these random forests, we tried to find which kind of models actually will be benefited of using of PCA. Now, because of the way that KNN works, if we have fewer dimensions to classify our data, we can actually do a very good improvement. And now, when we use PCA for reducing the dimensionality, we get same accuracy but a lot more faster results, as you can see in this table. Now, for the final metrics, remember that all of these models were trained on the global split that were train, validation, and test splits. And we can see that the best generalization is obtained in XGBoost and the random forest. And the other models cannot have enough accuracy on some of the digits.
So as a conclusion, we can say that the different techniques that we have implemented in these experiments not always give us the best results. Because this depends heavily on the dataset we are working with. Thank you for listening.